In this video, we will look at optimizing time, so using our time efficiently. So let's imagine that you're standing at the edge of a slow-moving river, which is 1 mile wide, and you wish to return to your campground, which is located downstream on the opposite side of the bank. So you can imagine for a moment that you have this river where you're on one side and the campground's on the other. Well, you're going to have to swim across the river. Would it be best to swim straight across and then go down, or swim partway across and then finish off by walking? Especially whenever you can swim 2 miles per hour and walk at 3 miles per hour. So let's take a look at this problem. For the sake of ease, let's go ahead and make the amount that we move down the river x. Then that means that the remaining amount is the amount that we walk, but that will be 3 minus x. Because the river is 1 mile wide, then we can use the Pythagorean theorem, which would say that 1 squared plus x squared equals c squared, which will mean that c equals the square root of 1 plus x squared. So the distance that we swim is 1 plus x squared. Take the square root. So let's take an inventory of what we know. So the distance to swim is the square root of the quantity 1 plus x squared. The distance to walk is 3 minus x. Now we know that time is distance divided by rate. So if we take the distance that we swim, divide it by 2, we get the square root of the quantity 1 plus x squared all over 2. If we take the distance to walk, which is 3 minus x, and divide by our rate of 3, we get 3 minus x all over 3. So that tells us that the total time is the sum of those two times. So t will equal the square root of 1 plus x squared all over 2 plus 3 minus x over 3. Now the domain of this function is dependent upon what values x can take on. So x could be as small as 0, which would mean that we would walk 3 miles. Or x could be as large as 3, which would mean that we would swim directly to the campground. So x is between 0 and 3. So let's now take the derivative. Maybe before we take the derivative, though, let's go ahead and rewrite t so that it is in a form that is going to be easier to differentiate. So we can rewrite the square root as a 1/2 power, and we can simplify that fraction 3 minus x all over 3 as 3 over 3 minus x over 3. But 3 over 3 is 1. X over 3 is 1/3 of x. So therefore, we can find t prime to be, well, we can use the generalized power rule and take the power times the coefficient and get 1/4, so 1/2 times 1/2, times the quantity 1 plus x squared, lower the power by 1. Now don't forget to take the derivative of the inside, which would be 2x. The derivative of 1 is 0, and the derivative of negative 1/3 x is negative 1/3. So t prime is going to be x over 2 square roots of 1 plus x squared, then subtract 1/3. Now we'll go ahead and find our critical numbers. And our critical numbers can be found, of course, by taking the derivative and setting it equal to 0, and then also looking at any values for which t prime isn't defined. So if we set t prime equal to 0, we get x over 2 square roots of 1 plus x squared minus 1/3 equals 0. If we set this up so that it's a fraction equal a fraction, in other words, a proportion, we would have this expression where we can cross multiply. So 3x equals 2 square roots of 1 plus x squared. Squaring both sides, we obtain 9x squared equals 4 times 1 plus x squared. Solving this gives us x squared equals 4 over 5. So x equals positive or negative 2 square roots of 5 over 5. But of course, x cannot be negative. So we have x equals 2 square root of 5 over 5 as a critical number. But then, of course, we always check to make sure that we don't have a critical number because the first derivative is not defined. So are there any values for which t prime isn't defined? No. There are none. So therefore, we only have one critical number, namely x equals 2 square root of 5 over 5. Now, determining whether or not this critical number corresponds to a maximum or a minimum, we could use the first derivative test or the second derivative test. But if you look at this first derivative, I don't want to take the derivative of it again. So let's go ahead and just use the first derivative test this time. So let's look at the first derivative test, and this means that we're going to look at where this function is increasing and decreasing and see if this function makes a turn at our critical number. So remember, whenever we do our first derivative test, we draw a number line that corresponds to our domain. So this goes from 0 to 3. And 2 root 5 over 5 is somewhere in the middle. Now, it might be beneficial to remember or to make note of the fact that 2 root 5 over 5, this is about 0.89. Okay, so that'll help us in determining our test values. So if I choose a value to the left, I can choose a number, say, like 1/2. And to the right, I can choose maybe a cleaner number like just 1. I'm going to substitute these, of course, into the first derivative. And if we put 1/2 into our first derivative, we obtain a negative number. If we put positive 1 in, we obtain a positive number. That means that our function goes from decreasing to increasing. So t is decreasing and then t is increasing, and that means that 2 root 5 corresponds to a minimum value. And that means that we have answered our problem. We just need to go ahead and write down our answer. So, therefore, if we answer our question, what route will take the least amount of time? The route that takes the least time is swimming to the point that is 2 square roots of 5 over 5 miles downstream.